Okay, in this video we're going to play with beams and look at some of the output from beams and look at some of the special options of beams to help you be ready for your homework on this coming Friday. What I have here is I've created 4 points in the XY plane. They are spaced a distance 5 apart, and I'm going to use those points to try a few different configurations of beam elements. So the first thing I will do is create a couple of beam elements by going to the beam tool right here. And these will be of type beam. I'm going to go point to point, and I'm going to click on the point 0 that's right there. Hold down control, hit point 1, with control down, hit point 1 again, and then hit point 2. I missed it, so point 2. So now I've got 4 points in there. Those 4 points are going to give me 2 beams. And material, I already have steel in this model, so I'll take steel. I'll leave that alone. That should be fine. And my beam cross section, don't have a beam cross section yet, so I'll click on More, New. We'll go with the rectangular beam with a B of 0.25 and a D value of 0.5. That'll make it a tall beam. Okay, and that should be everything I need here. And I have 2 beams with the tall orientation located as I had desired. Now I've got the beams. Now I need to decide on the kind of loading conditions that I want and the supports that I want. And what I'm going to do is basically make this first end cantilevered, and I'll leave this one like a ball joint. And so I can pre-select point 0, maybe, if I can reach it easy enough. Not as easy as I thought, but I can pre-select point 0, and then when I go into the supports, point 0 is already selected. I'm going to leave the ball joint constraints on, and I want this one to resist torsion. I especially want it to resist bending in the Z direction, and I'm going to go ahead and let it resist any bending in the Y direction as well. So I'm going to leave everything on this one. On the one up top, let's move it down a little bit. This point, point number 2, again I'll try to pre-select the point. Point number 2 selected, and I'm just going to constrain that one as a ball joint. So I'm going to turn off the moment constraints and say OK. That one's constrained like a ball joint. Now point number 1, I'm going to place a load on it here of 1,000 pounds in the negative Y direction, so I'm going to say negative 1,000. Okay, and there's my load. I believe I've assigned materials to this thing. I've got constraints, I've got loads. This should be ready to run. We'll do that. File, new static. I'm going to go ahead and set this down to about a 1% error. Leave everything else alone. OK, and we'll run it with a yes and a no and see the results. It's probably already done. Now it is done. The run completed. Let's take a look at the results, and let's especially see the deformed shape. That's what I want to see more than just about anything else. And looking at that deformed shape, it makes sense, I believe. Here's a cantilevered end. Let's go look at the front plane and see it a little more clearly. Okay, now we're looking at it straight on. Cantilevered beam in, sloping down a little bit. This joint is welded together. This angle should remain constant, which will have this one stretching but also bending and curving just a little bit. So that looks okay. Let's go explore some of the other options for viewing then. And let's first do a little bit of statics and get the reactions. But this was statically indeterminate. And so we're going to go from fringe type to model. Quantity, reactions at point constraints in the X direction. OK, and show. And we can see a 988 here and a 988 there. Very reasonable, I suppose. Actually, I've been playing, let me pop this up. I've been playing with MathCAD and doing Castigliano. And as a matter of fact, my Castigliano MathCAD gave me a 988.7 in the X and slightly less, 985 in the Y. This Castigliano was done at this top joint, so that 988 is a pretty good match. Let's go back and look at the Y direction. And my Castigliano gave me a 985. We'll change that to a Y direction. OK and show. And we have a Y direction. I didn't mean to do this, but I created a second window. Have a Y direction force of 985 here, and a force of about 1.4. Is that to have a? I can't tell if that has any numbers near the scientific notation. That's very hard to read. There appears to be a 1 there, so it's about a 15-pound vertical load. On this one, let's see, let me remember how to close these windows. I created it accidentally. Let's see. I'm going to have to go remember how to close these various windows. But that's okay. We're not going to stay here very long anyway. Matter of fact, to make it easy, I'm just going to leave it for now. Save current window, no. Then let's go back and look at a few other results. And so rather than fringes, let's look at some graphs. And one of the graphs that's interesting would be displacement graph. Displacement in what would be the local Y direction for the beam segments. And we will choose our beams. And I'm going to choose that beam, hold down Control, and choose that one. Over here, say OK. That will be treated as the beginning of our horizontal axis. OK. OK and show. And we see the bottom beam deflecting downward. Both of them having the same vertical deflection at this point, and then coming back up to zero deflection at the other connection point. So that one makes sense. Let's take a look at other things we could look at, including, rather than displacement, let's look at shear and moment diagrams. And I'm just going to leave them all on for now. No, that's really too busy. It's too hard to see. Let's look at the shear diagrams first. OK and show. And this says for the axial force, on the bottom member, we've got about a 1,000 compressive axial force. That makes sense. And on the top member, we've got closer to 1,500, which is two 1,000-pound loads combining together that are 90 degrees apart, combining together. That's very reasonable. Shear force in the Y direction on the lower beam is constant and tiny, and shear force on the Y direction on the upper beam is virtually zero, and shear forces in the Z direction are zero. That would make sense on all of these. Let's take a look at the bending moments instead. I'll turn off the loads and instead look at moments. And I would expect to see moments about Z only. I wouldn't expect to see anything about Y or X. Let's see if that's what we get. OK, and show. Somehow I'm not paying attention and I'm creating second windows. And so my shear and moment diagram, a torsional moment about X would be nothing, zero. Bending moments about the Y direction are zero. And here are my bending moments about the Z direction. We have a moment at the wall where this thing is cantilevered. That reduces and reduces and actually changes signs and goes to a positive 20. Notice where it connects to the other beam. The only reason there's a discontinuity because there's a change in the sign of the moment because the beam sort of flipped over. But it's same magnitude moment, so that's the moment that's being transmitted through that beam. and continuing up to the connection point at the wall with a moment of 0 because that had a ball joint on it. So that one makes sense as well. Let's see. We'll click in this window. Let's see what else is maybe worth looking at. Shared moment diagrams. Okay, we can plot displacement in the local y direction. We already have the beams. Let's see, window 1. That's OK and show. And so here's our deflection graph. We could do some hand calculations and check that. But there's the deflection graph. Let's look at what else we could look at. We could look at the slope graph. And so rather than displacement, we'll go with rotation. Rotation about the z-axis. OK and show. And our slope says 0 slope at the cantilevered end. And our slope of changing, and the slope does not quite go to 0 at the ball joint end, and it doesn't have to go to 0 at the ball joint end. And so we see slope diagram. Very quickly, is there anything else of great interest on the graph? Rotations. We could see strains and strain energies. We've already seen the shear and moment. The reaction isn't going to show anything because we don't have curves. So we'll just leave that behind, at least the graphs. We've already looked at the little bit we could see on the model. We could see the reactions that come from the model. I think that's everything we want to see here. What I want to do is change the beams and look at the system a little differently. So I'm going to go ahead and cancel that. Close this window. Save the current results. No. Now I'm going to make one change to the model. In this model, these two beams were welded together at this point, attempting to keep that angle fixed. What I'm going to do is put a beam release on here so that there is no moment transfer between these two, and then these ought to behave like a cantilevered beam connected with a two-force member. And so let's go make that change. And I'm going to go over here to Idealizations, Beams, and let's click on the correct beam. And I can release it from either end, okay? Or I could release it on both, but it's unnecessary. If I were to say that the right-hand end of this bottom beam is not capable of transmitting moments through this joint, so I release the moment transfer in the z direction, then that should achieve my purpose. Or I could say that because I know this beam starts here and goes to there, I could say the starting end of this beam also releases the moment. We'll just pick one of them. I'm going to go to beam 2, right click, edit definition, and go with beam release. There is none right now. We will say more, new, and this will be releasing rotation about Z is what I want to release. At some point I'm going to have to tell it which end to release. So that's a rotation about Z. Okay. Okay. Beam release 1. I know what I was looking for. Notice it says start and end. I've released rotation about Z at the starting point of this beam. That's not what I want to do. I'm going to set this back to none, and I'm going to go to end and set this beam release to beam release 1, which means no rotation about the Z transmitted, or rotations about Z are released. No moments translated about Z. So this is in effect a pin joint at this point. I'm going to say OK. We will run the model, and then we'll look for characteristics of a pin joint at that point. No and no. We'll see the results happening. The model has run. We'll go look at the results. Probably the easiest thing to look at is let's look at a graph of the bending moment. So let's go graph, shear end moment, And let's just look at all of the moments. Most of them should be 0. Moment about Z ought to be the only active one, but let's see what we get. Select the beam, okay, and I will pick both beams. I'll say okay, and point 0 is our origin, okay, okay, and show, and no moments here, no moments there, and I've got my 20 and 20 again, so I must not have actually done that release. Let me check it again, see how I have, see if I've made a mistake. Save the current window, no. And let's go Idealizations, Beams, Beam 2, Edit Definition. The end has Beam Release 1. If I click on More, Beam Release 1, Edit, I have clicked on the degree of freedom to release is rotation about Z relative to the beam axis coordinate system. That should be correct. And I released it at the end. That should be okay. Did I actually run successfully? I'll say okay here. I got beam release at this end. I'm a little puzzled that this thing transmitted moment into here. It should not have. Oh, that's, I see what it is. Did I put that release on beam 2? Edit definition. No release there. No release there. Cancel. Beam 1 is, okay, here's what I did. I put the release at the far end on this beam. Wrong beam. So I will select the bottom. So that did nothing. I already had a release there, so that did nothing. So I want to make sure that I'm on that bottom beam. Beam 2, edit definition. But that says, okay, that says beam 2, which is the bottom beam. The end release is there. Okay. But this one is highlighted. Bottom one is beam 1. Right click, edit definition, and it says beam 1. Okay, beam 1 has no releases. I'm going to turn on that release. Good. Beam 2 is the upper one. I'm going to edit in, or I'm going to remove the releases from beam 2. I had the beam release in the wrong place. Bear with me on this, but it's a mistake you might make as well. So beam 1, the bottom one, let's just check it one more time, has a release at its far end. Okay, this thing ought to run differently now and show the result. Run it. Yes. No. Results are happening. Now let's converge. Let's go look at the results. And we will look at graph of the moments. Shared moment. I'll turn off the shears for now. And let's just, got to pick the beams again. There. And hold down control. Pick that. Okay. Okay. Okay, and show. And now I have moment that changes with position within the first beam, but at the connection point to the second beam, there is 0 moment at that point, and there's no moment at all in the second beam because it's in effect pinned at 2 ends, and it's become a 2-force member with 0 moment in it. So all of that makes sense. Let's go take a look at some of the shears instead. We'll turn on the shears, get rid of the moments, and see what they have to say. We will OK and show. And so our Shear force in the Z direction, that's out of the plane. That's pure 0. Our shear force in the Y direction for this one is going to be a constant on the cantilevered beam, and there would be no shear possible on the 2-force member. And we're going to have an axial force on the 2-force member that's fairly high. It's at the 45 degrees, and we will have an axial force on our member that's cantilevered. Now, let's go back. Just take a look at this moment diagram one more time. And that would be moment about Z. I'm going to go ahead and leave the compression section on as well. OK, and show. So here we have bending moment at the cantilevered end that transitions to 0 at the connection point. Now let's go turn this thing into a simply supported or a pinned end, and so that'll make this thing a true pinned truss. And so we'll cancel this. Yes and no. And there are actually two ways I could make this end right here, which is cantilevered, behave as a pin joint. I could go back and modify my constraints and allow it to rotate about the Z-axis, and that's probably the best way to do it. But another way to do it is to place a beam release at the beginning end of this lower beam. And since I've already got a release on this beam, I'll select this beam, right-click on it, edit definition, and I will just take a beam release and place it at both the beginning and the end. So at both ends of this beam, I'm releasing any bending moment through that beam in the Z direction. Okay, we will run it, yes, no, the results are happening. We'll go take a look at our graph. We'll go again with graph of, let's look at moments, shear and moments. We'll just look at the moment. No, well, let's leave the P on. I expect some of that. I expect shear in the Y. I expect no shear in the Z. No moments about X, no moments about Y, but some moments about Z. And on the particular beams, this one, and hold down control, that one, okay, 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 and show. Oops, somehow I didn't get it. I either forgot to turn on the release, didn't save it, or maybe the release didn't override the constraint at the end. That's interesting. That surprises me. I would expect either one to work, but I will tell you I was just guessing. I hadn't tried it both ways. So, no, let's go look more carefully at this beam, that beam. Let's make it red. Right-click, edit definition. I do have the beam release at the start of this beam and at the end of this beam. I would expect that to work, but it doesn't. And so I'm going to go ahead and set this back to none. Apparently the constraint totally overrides the beam release, and so I'll just need to go edit the constraint at this end. Right, make it red, edit definition, and I'm going to release Z rotations on this beam. Okay, run it, yes, no. The results should be done. They are. Go to here, go to graph, and shear and moment. Turn off the ones that, let's see, axial load. I would expect shear in the Y, but not the Z. And I would not expect either of these two moments. And we got to pick the beams again. So I pick the beams, hold down control, okay, 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 and show. Okay, now all of these moments are virtually 0. Anything that's not 0 in all of these moments, that's just round off error. Same kind of thing is true for shear forces in the Y. Why is that? Because these are now both 2-force members. So there's not going to be any shear force in the Y. That's 10 to the minus 13th. That's round off error. All we have is axial tension and compression. in the two force members. So that's probably enough for now playing with this beam.